Okay, let's get started. So this Monday we talked about some classical symmetric encryption techniques, including substitution cipher and the transposition cipher. We talked about Caesar cipher and Virginia cipher, how they work and why they are not secure. So we proved that even with very large key space, those ciphers, they are still easy to attack. So crypto analysts, they don't really need to get the key, compromise the key, to extract the plain text from the ciphertext. So the fundamental reason behind that is the ciphertext coming out of those algorithms, they always bear some statistical relationships to the plain text. So crypto analysts, they can use that statistical relationships to guess the ciphertext without knowing the password or the key, sorry. So the question we will ask is there any perfectly secure cipher? So what do we mean by perfectly secure? We mean that the ciphertext bears no statistical relationship to the plain text. So the only way to extract the plain text from the ciphertext is to compromise the key. So actually, in theory, there is such thing, one-time pad cipher, and this cipher is proved to be perfectly secure. So how does this cipher works? So in this one-time pad cipher, the truly random key is as long as the message you want to encrypt. So the encryption is very simple. It's just doing an exclusive OR. But the key has to be truly random and as long as the message. And the key used to encrypt can only be used once. If you use the key to encrypt this message and you have to discard it, you cannot reuse it. And each message requires a new key of the length as the message itself. For example, let's take a look this example. We have a plain text in letters, hello world, and more letters coming. And we are doing a shifter cipher. So here, the key is different for each letter. So this is different from Caesar cipher, because in Caesar cipher, the key is always the same. We shift the letters to a constant distance. And this is also different from the simple substitution cipher we discussed on Monday, because the simple substitution cipher, even though the key space is huge, there is still a fixed mapping between a plain text letter to a ciphertext letter. However, in one-time pad, the keys 1, 25, 8, 7, they are totally independent. So this cipher is perfectly secure in theory. So this cipher was actually the first mentioned in 1990s by the gentleman Gilbert Verman. So in some literature, this is called a Verman cipher as well. So he got this patent states that a cipher in which each letter in a message was electronically combined with a letter on a paper tape key. So the problem here is the paper tape key cannot be arbitrarily long, and maybe it cannot be truly random. But then later, U.S. Army Captain Joseph, he realized that if the key character sequence, they are completely random, it will be hard for crypto analysts to crack this. However, he cannot prove that. He can only find that this is hard, but he doesn't know how hard it is. He doesn't know this is perfectly secure. So then in 1949, Shannon, in his historic paper, Communication Theories of Secrecy Systems, he actually proves that this kind of cipher is perfectly secure. So in order for Shannon to prove this, actually he invented a theory called information theory, which is the foundation for our modern communications. Information theory is actually one of the hardest course I have ever taken back in college. So we're not going to prove this today. But I will give you some sense why this is perfectly safe. So basically, this kind of a one-time pen cipher can produce random outputs that bears no statistical relations to the plain text. Because this ciphertext has no information whatsoever about the plain text, except that the key length we know, and the key length is the same as the plain text length. So there is no way to break this code. So for any given, in other words, for any given ciphertext or plain text, they are equally possible. So this is basically the fundamental reason why this is perfectly secure. But Shannon proved it using his information theory. So since this cipher is so perfect, why we are not using it? The reason is very simple. Even though it's secure in theory, it's not practical. It's very hard or impossible for us to construct something like this. There are two requirements to construct this one-time pen cipher. First, we need to generate arbitrarily long, truly random key values. And this might be surprising to some of you, but generating truly random numbers, it's a very difficult job. So actually, if you did some C programming, you might have been using the rand function to generate random numbers. But all those numbers, they are actually pseudo-random. They are not truly random. There still are some statistical features cryptanalysts can utilize. And another problem is to use this cipher, we need to securely send this key to the receiver, so the receiver can use it to decrypt the message. However, this key is big. As long as the data, the information you want to transfer is big, they're the same size. So how can you securely distribute this key? It's very difficult. There is no secure way to do that. In theory, the secure way to do that is to use another one-time pad to encrypt that. So it never stops, right? That makes sense. So this perfectly secure cipher we cannot achieve in reality, but we have some better approaches that are better than the classical cipher we discussed on Monday. So in the modern cipher, because we assume that all the encryptions, decryptions, and the cryptanalysis are going to use computers, so those ciphers, they actually operate on bits. They do not operate on letters. So previously, the Cipher cipher and the Virginia cipher, they operate on letters. And modern ciphers, they combine several classical ciphers together in succession to make the cipher harder to break. So this part is also hard to prove. So again, Shannon proved this in 1945, that even though we showed that those classical cipher techniques, they are not secure, but if we combine them together, it's much harder to crack. And this new type of cipher is called product cipher. So we are going to show several examples of this product cipher, and you can clearly see that they are just using substitution and the transposition. So in this 1945 paper, Shannon formulated the principle of confusion and diffusion. So you are actually familiar with this concept. Confusion is just substitution, and diffusion is just transposition. So because modern ciphers, they operate on bits running on computers, so the substitution cipher we're talking about here, they will take n bits as input and output another n bits using the lookup table, maybe also look up the keys. And this lookup table is called the S box, substitution box. And the transposition cipher do the same thing. Take in n bits, permute using another lookup table, and that table is called a P box, permutation box. So we can see that later the flow of several block ciphers, they are just the combination of S box and P box. So the modern encryption algorithms can be divided into basically two categories. Symmetric key algorithms. So far we have been focusing on this part, and maybe this Friday we're going to talk a little bit about symmetric key crypto. And this symmetric key crypto, there are block cipher and stream cipher. And there are some method that has been successful in designing those block ciphers like Pfister or SPN. SPN actually stands for Substitution Permutation Network. And the stream cipher, we have truly random, which is like the one-time pad, which is not possible to achieve, at least for long, and pseudo-random. So let's discuss what is block cipher and what is stream cipher. So block ciphers, they take a number of bits and encrypt them as a single unit. So if the plain text is not a multiple of the block size, we have to give some padding there. And a stream cipher encrypts one bit of the message at one time. So you can see the stream cipher as a very special case of a block cipher in which the unit is just one bit. So to use this block cipher, we have to partition our data into many sections, and each section is only the same size as the block cipher, the block size. So if our data is not a multiple of the block size, we need to do some padding here. And in a very good block cipher, so each output bit should be a function of all the input bits and all the key bits. So it should not just rely on some certain bit, because it will be easier to give away some statistical information. So there are maybe less than 10 widely used block cipher algorithms. They are all open. And the first one we're going to talk about is called the Data Encryption Standard, DES. It was developed in 1970s at IBM. DES has a block size of 64 bit and a key size of 56 bit. And DES is already considered insecure. So we're not supposed to use it anymore. So here is a flow, is a snapshot of the flow of DES. So you can see there, these are things you are familiar with. They are just the S boxes to substitute bytes and another P box to transposition the bytes. So we're not going to dig into the details how they design the X box, how to design the permutation box. I'm not really an expert of that. So one problem of this DES has also the reason why it can be easily cracked is its key size. It's only a 56-bit key. So it's pretty easy to do a brute force attack on DES with our modern computers. So that's why maybe around 2000 or maybe a little bit earlier than that, they standardized another crypto algorithm called triple DES, which basically is just to run DES 3 times. But they're not running 3 encryptions here. They are doing first encrypt the plain text with the first key and decrypt it with the second key. Obviously, this decryption will not generate the plain text because the keys are different. Then they encrypt it again with the third key. The reason they are not doing 3 encryptions but do encryption, decryption, encryption is because they want to make it backward compatible with DES. So since there are 3 keys used here, there are 3 keying options in the standard. Obviously, there are more, but in standard there are 3. First, all 3 keys, they are independent. If all 3 keys are independent, we have a total key size of 168 bits. And another way is make key 3 equals to key 1, but key 2 are independent from them. So in that case, the key size is 112. And the third option is use all 3 keys, make them the same. So in this case, let's see what will happen. We will encrypt with the key. We get the ciphertext. We decrypt it again, use the same key. So we get the plain text again. Then we encrypt it again. So this is exactly the same as running DES once. So the reason they do it is this can make 3 DES backward compatible with DES. So if you have a 3 DES implementation, you can actually make it run like just a DES. Another very popular block cipher algorithm is called AES. This is also proposed around 2000, I guess. So AES stands for Advanced Encryption Standard. And it has a block size of 128 bits. And it can support 3 different key sizes, 128, 192, and 256. So from this snapshot of the flow of AES, you can see these are the substitution S boxes, and the shift here, they are the transpositioning. So basically, even if those modern block ciphers, they are much more complicated than the classical ones we discussed this Monday, they are still just a combination of them. So there is a problem in using this blockchain, this block cipher. Block cipher, we know that each block for one algorithm, it has a fixed length. For example, for AES, it's 128 bits. So when we want to encrypt something, we need to partition our data into smaller segments like this. Then we can encrypt each plain text segment, each plain text block using the AES or DES. But the problem here is if the plain text 1 is the same as the plain text 3, then the ciphertext 1 will be the same as ciphertext 3. So this doesn't really hide some statistical information. So here is an example. So we have a Linux penguin here. This is a plain text. So we encrypt this figure with the way we described it just now. Each block is encrypted independently. Then on the right-hand side, we have this encrypted figure. So you can see, even though this is encrypted, you can still see the shapes of the penguin. It still gives you a lot of this statistical information there. And also, this blockchain, this block cipher is also vulnerable to replay attacks. So I'm going to use one example to explain what is a replay attack. So let's assume Eve works in a company a few hours per month, which means her salary is really low. But Eve is smart. She figured out her company used several blocks of information for each employee, and this is the encrypted block information, and she figured out that the fourth block is the amount of money to be deposited in the money's account at the end of each month. So for example, Adam is a full-time employee at Eve's company. And this is what Adam's encrypted information looks like. And this part is amount of money, the salary, and Eve has the same thing. So at the end of the month, Eve can intercept the ciphertext sent by her company to the bank. So she can first intercept the ciphertext of Adam's encrypted information and her own's. Then he would replace her own block 4 with Adam's block 4. So he get the money, she gets the money she doesn't deserve, because that is the amount that Adam deserves. So interesting thing here is, in this replay attack, Eve didn't really crack this algorithm. She doesn't know how much Adam makes. She doesn't need to know that. What she knows is Adam is a full-time employee. She must make much more than I do. So without breaching the confidentiality, she can get more money than her deserve. So this is a replay attack. So in order to solve this problem, obviously we cannot encrypt each block independently. So NIST, the National Institute of Standardization, they published several, they call it mode of operations of block cipher. So the first, the simple way we discussed just now is called electronic codebook mode. And there is another mode called cipher block chaining mode. And this is the mode that is used in encryption. So if you are encrypting a file, if you are encrypting the message during communication, or you are encrypting all the full storage, and maybe you are using this mode, not the ECB mode. And they also published 3 more modes to make block cipher as a stream cipher. So we're going to talk about what is a stream cipher in a moment. So all these modes of operations, they have been advised to encrypt any information, any size, using all kinds of algorithms, either DES, AES. So if you want to encrypt something, what are the parameters you need? Obviously, you have a key, you have the plain text, and also you need to choose which algorithm you want to use. But that is not enough, because many algorithms, they support different key size. So you also need to choose what is the key size I want to use. Obviously, if you choose a longer key, it will be harder for attackers to brute force. Besides that, there is also this mode of operation you need to choose. So here I took a screenshot of OpenSSL on my laptop. You can see that these are the encryption algorithms available on my laptop. You can say AES with 128-bit key length in CBC mode. And you can also say AES 192-bit with ECB mode. So let's talk more about the ECB mode. So ECB mode message is partitioned into independent blocks, and all of them are encrypted independently. So each block, in this case, so each ciphertext block is only determined by the plain text block and the key. And the same plain text block will always produce the same ciphertext block. That's why it's kind of like a substitution there. So that's why this mode is called electronic codebook mode. So it's like looking up a substitution table, even though that substitution table goes through a lot of calculations. And in that Linux Penguin example, we see that this mode is not secure for transmission big data, but we can still use this mode to transmit some very small data. For example, we can use it to transmit keys. And why we can use it to transmit keys? Because normally keys, they are the same size as the block size. So you're just doing one block. Or even if the keys are longer, there are maybe 2 blocks and 3 blocks, but the keys, they are supposed to be totally random. There should be no repetitions in keys. So we don't worry about transmit keys using this ECB mode. So this is a flow of how this ECB works. First, the plain text blocks, we have many. Then for each of them, we just encrypt with the same key. And we generate the ciphertext, then concatenate them together. So in order to solve the problem we mentioned before, we have this cipher block chaining mode. So this is a technique in which the same plain text block, if repeated, will produce different ciphertext blocks. And all the blocks, they are linked together in encryption mode. So in this mode, each previous cipher blocks is chained with current plain text block. And however, and this is widely used for data encryption. And this is a flowchart of it. First, we have a plain text block. We perform an exclusive OR with an initialization vector because at this moment we don't have previous cipher blocks. Then we encrypt this together with the key, generate the ciphertext block. Then the ciphertext block is fed back to the system. It is used for exclusive OR with the second plain text block and encrypted again. So here we are introducing something new, is the initialization vector. So this initialization vector is not a key. It doesn't have to be protected as a key. However, the receivers, they do need this initialization vector to correctly decrypt the message. So this IV should be transmitted to the receiver side. However, if we do a plain text transmission and we let the attackers knows what the IV is, some research already showed that the attackers, they can pull off all kinds of tags using this. So actually, normally what we do is we will encrypt this IV using ECB mode, the basic mode. And as we can see, the size of the IV is the same as the block size. So here is a comparison of using the ECB mode and CBC mode. This is a plain text. This is encrypted using ECB. We can see the pattern there. And this is a CBC mode. Because of the feedback, the statistical patterns are hidden from us. So you can clearly see the difference. So this is why we are using this for encryption, not this. So there are some advantages and disadvantages of CBC. First, the advantage is each ciphertext block depends on all blocks before it. This is an advantage. This makes each block harder for attackers to attack. And any change to one block will influence all following blocks. But the disadvantage, like we said, is we need this initialization vector. It has to be known to the receiver and sender. And we cannot really send it in plain text. Usually we will encrypt it in ECB mode. So the next part we are going to discuss is stream cipher. So stream cipher process message bit by bit, not several bits forms a unit. So the encryption part of the stream cipher is extremely easy. We just do a exclusive OR with the plain text and the key bit by bit. And you can see that this is the same as what we discussed in the one-time pad. So the tricky thing is how to generate this key. If we can generate the key as the one-time pad required, if it's always truly random, if it can be arbitrarily long, this is kind of like the one-time pad. Of course, there is still the sharing problem. So here it is how it works. This is a plain text, bit by bit, and the key stream. We just do exclusive OR to generate the ciphertext. So the randomness of the key can completely destroy the statistical properties in the plain text message. That's why this is safe. So the key point here is how to generate this cipher key string. And there is not a very good way. So we are using block cipher as the building block to build a stream cipher. So if we use block cipher in this cipher feedback mode, the encryption and decryption use the encryption function of the block cipher. So we have our IV here, encrypted with the key. Then we get the ciphertext. Then we choose maybe S bit of this ciphertext. Then discard the rest of it. Then we do an exclusive OR using this S bit with the S bit of the plain text. So if the S we are choosing here is 1 bit, so each time we are just encrypting 1 bit of the plain text. Then the result is feedbacked back here and shifted and encrypted again and select S bit, discard some, then do this. So if it's just 1 bit, then we are encrypting 1 bit by another bit, one by one. So the advantage of this mode is we can use this mode to build a stream cipher, obviously, and the result is feedback for next stage. So there is a propagation there, and it can allow any number of bits: 1 bit, 8 bit, 64 bit, denoted as CFB1, CFB8. Obviously, if we are using it as the bit size we choose here equals to the block size, it will be very efficient because we are not going to discard any generated ciphertext. So if you can hear, so in that case, if the block size is the same, if the bit size we are choosing is the same as the block size, it is actually the same as the CBC mode. So this is a widely used approach to generate string data encryption. One problem of this CBC mode is that error propagation there. So this feedback, which is good for security, however, if there is one transmission error there, it will propagate to all the following blocks. So the receiver side may not be able to decrypt the following bits. And there is another mode that can avoid this error propagation. It's called output feedback mode. So in this mode, there is a nonce. So nonce means number used once. So the reason they say nonce here instead of IV, maybe is because this doesn't have to be secure. I'm not sure, maybe, yeah. So they encrypt the nonce with a key, and this part is feedback to the next round to be encrypted, and then the result is doing exclusive OR with the plain text and generate a cipher. So here we don't need to choose how many bits we want to encrypt each time, but still this. So you can see that actually this part is kind of independent. It doesn't really relies on the plain text. They keep generating ciphertext, and this ciphertext here, this ciphertext only relate to nonce and key. So we can generate all those ciphertexts at this step in advance. Then we can just do a simple exclusive OR here to encrypt the plain text. So obviously, the benefit is bit errors would not propagate, and you don't. So actually, it was specified at the beginning with n-bit feedback. However, some research showed that it's not secure to do that. So right now we are just using the full block feedback. The last mode we're going to talk about is called counter mode. So counter mode is very similar to the previous modes actually. So first of all, it's simple. There is no feedback. Since there is no feedback, you can calculate all these ciphertexts here at the same time because there's no feedback. You don't need to wait for the previous ciphertext to calculate the next one. And there is a counter. So this counter should be secure, but however, it doesn't have to be the relationship between counter 1 and counter 2, maybe just +1 or +2. So they do not have to be independent. So the counter is encrypted with the key, and the result with the exclusive OR with the plain text, we get the ciphertext. So counter mode is similar to the OFB mode without the feedback, and because there is no feedback, it can be used at very high-speed network encryptions because you can do all the blocks at the same time. And this is actually used in some protocols. For example, we're going to talk about this protocol maybe next week. This is part of the IPsec, Internet Key Exchange Protocol, IKE version 2. So they are using AES in this counter mode to exchange keys. So advantages of counter mode, it's very efficient. You can do the encryption on all the blocks at the same time. And you can randomly access encrypted data block. And it is proved as secure as other mode, even though this mode looks simpler than other modes, but it has been proved the security guarantee is the same. So here is a comparison of all the modes we discussed today. EC, electronic codebook mode, which is used for block cipher, and CBC mode, cipher block chaining mode, and which can hide the data pattern there, and the other three modes, CFB and OFB and CTR for stream cipher. So we talked about that using the block cipher as a building block to construct stream cipher. But actually there are some other algorithms. They are stream cipher and they are not based on block cipher. And one of them is called RC4. So R stands for run request. C may stands for crypto, I guess. So he designed many very influential cryptos, including RSA. We are going to discuss in the next class. And this RSA4 is a widely used stream cipher in our Wi-Fi web and also SSL. So next class, we are going to talk about what is hash, what is MAC, and how to do key management for symmetric key crypto. And hopefully we can start discussing public key crypto.
Is the lab due on Sunday or the assignment due on Sunday or the assignment due on Sunday?